My name's Andrew Richards. I'm the founder and CEO of Codeplay, and I was chair of the SYCL industry standard, which is now the programming model for One API. And I run Codeplay, and we're big believers in industry standards for high performance computing and AI. And in this session, we're going to have other people talk about high performance computing from the national labs, but we've invited you here to talk about AI because you're integrating One API and various other hardware into TensorFlow. So we're really interested in that. So can you give a bit of an introduction to who you are and what you do?
Sure. Yeah. First of all, thank you for inviting me here. I'm honored to be here. And yeah, so my name is Penporn Koanantakool. I'm a software engineer at Google. I work on TensorFlow's integration with hardware vendors and also TensorFlow kernels in general. And like Andrew mentioned, so I lead TensorFlow's integration with One API. Yeah. So it's not just for Intel hardware, but also for ARM as well. We use One API for both x86 backend and also ARM backend, and also to support Intel XPU devices in the future.
So that's interesting. You're using the same library and program model, One API, for lots of different hardware. So are you using it for Intel CPUs, Intel GPUs, and ARM?
Yeah, so it started with just Intel CPU. So yeah, so we have a close partnership with Intel, and then the whole One API effort started, and we started integrating with it was MKLDNN at first, and then MKLDNN became OneDNN, which is part of One API standard, One API deep neural network library, and we were doing that for Intel CPU. And then OneDNN added the ARM backend. So we also benefited from that because the integration with TensorFlow and OneDNN is already done. So we can just compile the option with ARM backend. And now we also get TensorFlow support for ARM.
Yeah.
And right now we are also working on supporting Intel XPU devices, which will also use both DPC++ and OneDNN underneath. But we are approaching it differently. So for CPU one, we add OneDNN integration code directly into TensorFlow repository, but for the XPU devices, we are making it a plugin. So it will be a separate binary and talk to TensorFlow through a stable binary interface.
Right. So there's going to be lots of different hardware all integrated into TensorFlow via a kind of single standard. So do you use One API or do you use the SYCL standard? Because SYCL is part of One API, but One API contains a larger amount of things like OneDNN.
Yeah, so on the TensorFlow CPU side, we are mostly focused on OneDNN. So we don't go and code in DPC++ directly. We mostly just call OneDNN API from the TensorFlow. So it works like this. So we write custom ops for TensorFlow, and these custom ops will call OneDNN primitives. For example, convolution primitives and whatever. And these users cannot call these custom ops directly. So these custom ops get introduced into TensorFlow graph by a graph rewrite pass. So when we run the graph rewrite pass, it will go through vanilla TensorFlow ops and see what's available, and then swap that out and then replace it with OneDNN op. And those OneDNN op will be run. So the user won't have to code in DPC++ or even code in using OneDNN primitive directly. So they just need to call normal TensorFlow op, and then we will call those custom OneDNN op underneath for them.
Right.
Okay. Is just to turn on one environment variable flag, and then we will turn on that graph rewrite, and we write all the applicable ops to OneDNN ops.
I see. So you rewrite the ops to be OneDNN ops, and then they'll work within TensorFlow. Gosh, that's interesting. So, but there's quite a lot of different operations in TensorFlow. So how do you manage to support so many different TensorFlow operations?
Oh, so we just focus on computationally expensive ops. So ops like contraction-like ops, for example, matmul, batch matmul, convolution 2D, convolution 3D, and all kind of fused version of those, fused matmul, fused convolution. And then we extend it to quantized version of those as well. And yeah, and then all the other operations that are fusible, ReLU, fuse batch norm, and other stuff.
All right. So what do you mean by a fusible operation?
Oh, we mean they can be done together in one step. For example, convolution or contraction ops with element followed by element-wise operations. Those actually can be done together in one kernel. You don't need two separate kernels, and that can save you cache memory access time, because if you just do convolution first and then do that element-wise operation later, the things that you were already doing in convolution, your tensor might fall out of cache, and you may have to reload the whole tensor again for just those element-wise operations. So by fusing them together, you can just apply those element-wise operations while you're just doing that one block is still hot in cache.
Yeah, so that's going to give a huge speed improvement, isn't it, if you can combine two or fuse two operations together, because the amount of time taken to move data off chip and on chip, especially for hardware that doesn't even have a cache. Sometimes we see hardware that doesn't even have a cache, so you really want to keep that data on the chip.
Yeah, and in fact, we don't just fuse two ops, we fuse as much as possible. And so there can be multiple operations. For example, maybe ReLU, and then you requantize stuff, and you can fuse as much as possible. And as long as it's not like two convolutions together, and that would be hard to fuse, because now it's not just block by block operation now.
Yeah. So that fusion sounds like quite a complicated thing to do. How do you fuse two operations that were written separately together?
So it started by manually adding the fusion patterns. So both the TensorFlow and Intel TensorFlow side look at models and see what patterns happens the most, that would benefit the most when we add the fusion, and then we manually add the fusion pattern to look for and the fuse ops. But we are trying to approach it more systematically. So in the future, we will fuse those by compiler. So the compiler will detect what is fusible and generate the kernels for those.
Right. So you talk about generate the kernels, because I suppose for a lot of people you would expect to hand write all of the kernels, but can a compiler is it possible for a compiler to actually generate kernels?
Yes, it can, and then we are actually already doing that with MLIR and TensorFlow. Yeah, we did it with a small number of kernels, but we plan to expand it more in the future.
Gosh, so that sounds like quite complicated compiler magic that's going to generate kernels for you. Is it able to achieve the same amount of performance that you could do it by hand, or how can it be faster?
Oh, that's a good question. Yeah. So I guess, so so for the ones that we have a direct comparison with, we only deploy the compiler one when we know it's faster. Yeah. But for the case that that the handwritten kernel is faster, there's no reason not to use handwritten kernel. So we have two paths. And we have the option to go to either of them. And also for the fuse patterns that we don't have handwritten kernel for, we can also fall back to the compiler option to use it.
Yeah, gosh, it's so interesting that you've got multiple different ways of doing the same thing, and then you measure which one's fastest, and you go, we'll do this one or this one depending on what's fastest.
That is the future plan. So right now it's still kind of like not that automatic. It's more like heuristic, but yeah.
Yeah. Gosh, so is the vision with MLIR that you are going to generate kernels rather than stitch together handwritten kernels for each processor?
For which processor?
So to MLIR, it is about generating kernels rather.
Oh, so the question is, what is MLIR about?
Yes, I suppose so. Yes.
Oh yeah, so MLIR is actually used both as a code generator and as a graph compiler for TensorFlow. So it can go look into the graph and fuse the ops and rewrite and cluster all the ops together, and it can also generate kernels.
Right.
Yeah, and it has And because so MLIR stands for multi-level intermediate representation, so it has multiple levels that we can intercept at any level. For example, we have from the op dialect, TensorFlow op dialect, we can lower it down to linear algebra, lin-alg dialect, and from lin-alg dialect we can lower down to vector dialect, which will lower down to more architecture-specific vectorization, like maybe Intel AVX512 dialect, AMX dialect, or ARM SVE dialect. Or we can actually intercept as the linear algebra dialect and go directly to vendor-optimized library as well.
Right, okay.
So that's where the choice comes from, yeah.
Yeah. So if there's some new hardware company that wants to support MLIR, does that mean they have to have a compiler backend that lets you generate code for their processor?
So they can, yeah. So I think a good option is to add a dialect that will connect to existing dialect, and MLIR is actually relying on LLVM. So it's part of the whole stack. So you can intercept anywhere you want. Yeah, but most common one is to add your own dialect that I've seen.
So it sounds like there's a lot of stacks in the compiler going, I suppose that's what MLIR means, multi-level. It's all sorts of things going down through the compiler through all these phases. Does that not add a lot of overhead in terms of performance?
So we have bought ahead of time compilation and also just-in-time compilation. I don't actually work directly on MLIR, so I can't tell you the actual overhead of it, but from the usage that we've seen inside, the overhead is not that high. Yeah.
Oh my gosh. Okay. No, it's all really interesting. So so what industry standards do you see important with TensorFlow? Do you engage with industry standards much, and which kind of industry standards do you think are important?
Oh, the first thing that comes to mind is the MLPerf standard. Have you heard of it? So yeah, it's the industry standard for machine learning inference and training benchmark, and I think it's great because it allows people to measure their progress in a systematic way and also compare efforts together, and it helps push the envelope, push the limits of what hardware and software infrastructure, in machine learning. The other standard is probably ONNX, so the Open Neural Network Exchange format. So that one allows people to run models on any framework that support it. TensorFlow also has a converter to and from ONNX model. So, and from ONNX model, there are many other executors that support it. MLIR also actually support ONNX as well. We have like a compiler that will compile ONNX model directly to programs that will execute through MLIR.
So you're integrating a lot of different technologies together. How do you make sure that all of the things work together?
I think we are relying a lot on the community on that because we also have a limited number of people and we cannot just go and expand and work on everything that looks interesting. So yeah. So I think it depends a lot on the community and what they care about. So I think they go hand in hand. So if the community cares a lot about it, they also want to contribute more of it and then add more features into those things. So I think it's a nice balance. So things that not many people wanted to use, then maybe not many people wanted to add code into it, and that's probably okay. And the things that a lot of people care about, we get some development going. Yeah.
Yeah. So it sounds like it's very important for TensorFlow to be part of a wider ecosystem.
Yeah, because the ML field is moving so fast, and it's a lot of work to catch up, even with all the community's help. Yeah.
So you see the ML community is moving very fast, but then some people talk about this idea called AI stabilization, the idea that we've invented all of the operations that we need for AI, and so there's no need to do anything new. So do you think one of those is right, or is it that we have invented all the operations? What is it that ML people are doing that causes so much fast movement?
I can't claim to be an expert here, but from my personal point of view, I I think we are far from being done, both on the ML research side and also infrastructure side. So on the research side, so it's not just like, oh, we have all the operators, but it's more like how do we achieve our goals with machine learning, and right now it's not smart enough to do the generic things that we want it to do yet. And then there's also a question of ML fairness or ethical AI. How do we actually take the bias out of the model when everything we train with is actually biased? The data we take in from the internet is all biased, and how do we make a fair model and not make people suffer from the consequence of it not being fair? There's also a question of interpretability. For example, if you use it in healthcare and then some ML model just say, oh, you have a higher chance of being dead in the next year or something, then people would want to know, why are you saying that, and not just like, oh, it's because the math say so. So there's still a lot of work we need to do on the ML research side, on how to get it to do something more useful and also more fair to humans. And there's also on the side where, how do we get it to do things more efficiently? So we are scaling model larger and larger now, using more and more data, but maybe we should try to use data more efficiently, learn more from the amount of the data that we have, maybe construct model in a more efficient way as well. And for example, another way is doing sparse training. So all the weights don't need to be dense because not all of them are important. Like, for example, if you look at the human brain, the connections are actually sparse. So then, you can try to save more computation by doing sparse training. And then the question is about, how do you make it train efficiently? How do you know the topology of the connection then? How do you learn them? And that's just on the machine learning side. And then there are a bunch more on the infrastructure side, but hardware and software.
Yeah. So if somebody gave you a new processor that could do AI faster, but it wasn't programmable, so you couldn't write new kernels or anything like that, would that be worth it? Like, how important is programmability versus performance for new hardware?
So you are relying on just existing code? And on that hardware? I don't think that would be scalable with machine learning. Researchers come up with new operators all the time for new models and new ways to do things. So it's very important that it's very programmable for them.
So one of the libraries that you haven't talked about, but we've dealt with quite a bit, is this Eigen Library. How important is Eigen for TensorFlow? Is it going to be replaced by MLIR, or is it still being used?
So we are relying on, so historically, Eigen is very, very important to TensorFlow, and it is still right now. In the future, we do see transitioning off some of the Eigen kernels off to MLIR, because, let me give the audience some background. So TensorFlow uses Eigen for all math kernels, so it relies on Eigen for data type and also for all element-wise and convolution contraction operations. Those are run through Eigen kernels. And we rely on Eigen's ability to generate, to vectorize for multiple architectures with just one abstraction layer, which is Eigen packets. And we rely on that to compile TensorFlow to be able to target on multiple vector architectures. But our issue with that is Eigen doesn't have dynamic dispatch right now. And with TensorFlow, TensorFlow package is compiled into one Python package, and we need to compile with just one architecture, and so we have to pick just AVX, compile with just AVX vector instruction, just so the Python package can be run on a lot of hardware available right now. But that also means that we cannot use AVX2 and AVX512 on newer processors. So that's one issue with Eigen, and right now we are alleviating that by making Eigen call 1DNN matrix multiplication routine, which has JIT and can JIT those newer AVX instructions underneath. So we are mitigating that with 1DNN manual, and also with 1DNN custom ops, which customer can choose to turn on, and that one will have more power on using newer instructions. Another issue with Eigen is that it's a template library, so you have to compile everything ahead of time, and it can take a lot of space, and TensorFlow covers a lot of possible data type that user wants to use, but not all data type needs to be used for the same user. For example, one user might just want to use int8, but we actually have to compile everything with the templated library, like compile int8 kernels, we plot 16 kernels, floating 16 kernels, floating point 32, and a lot more. So with compiler, we can just generate what the user needs. We only need to keep the most commonly used kernels in the wheel, but then when the users calls rarer kernels, we can just generate them instead of put everything in the wheel and make the TensorFlow file too big.
Yeah. So it sounds like Eigen causes you a lot of challenges, but at the same time, you can't completely replace Eigen yet. It'll take some time before you can completely replace it.
We are still using Eigen a lot. We are still using it in many places in TensorFlow. We are also using it for thread pool. So we added a thread pool interface in the unsupported folder of Eigen, and Eigen thread pool is used as the basis of the whole TensorFlow thread pool. So a lot of TensorFlow components is relying on Eigen, and we are just trying to replace some functionality that we think MLIR can help leverage the existing issues.
Gosh, so there's lots of interesting challenges going on. It sounds like such an exciting project to work on, and such an exciting field to work on. Unfortunately we've run out of time. I would love to talk to you more. We've run out of time, but Penporn, thank you very much for joining us.
Thank you so much, Andrew, for your time. Yeah, and for inviting me.